Hey folks, so we're getting into the meat of chapter 12. We're talking about torque. We're talking about that rotational force. We're going to apply a force on something off axis, right? Off axis from the point of the pivot, and that's going to start to make this thing spin. What is this thing? Well, it could be anything, any object. But if we think about the story that we're building, we've taken some time to talk about angular acceleration. We knew about that back in chapter 4. And now we know that we have some sort of rotational kind of inertia, this moment of inertia, I. So if I have I, and that's very similar to m, and alpha is very similar to a. In fact, actually, we're building up an entire list of quantities, right? If I think back now to what quantities we're talking about in the linear and angular listings, we have position, which is x in linear space. It's theta in angular. Velocity is v in omega. Acceleration, a, alpha. Inertia is going to be mass, m, or moment of inertia, I. And with force, we're talking about F and torque. And torque is going to be this tau. It's a it's a lowercase tau, which I kind of draw as this. Right? And people draw taus very differently, but this is my tau, which is going to signify torque. Right? Torque is like a rotational force. It makes things go, clockwise or counterclockwise. It makes things spin. Torque, by the by, has units of Newton meters, and Newtons times meters in the past has been joules, but this is not a joule. All right, we don't call the unit of torques joules. We call it Newton meters. And that's that. They're fundamentally different. Torque is a vector. Torque. So we'll talk about that in just a second. But I want to start to build this up, right? I want to talk about the forces on. Let's try and draw that sigma again. There we go. The sum of the forces on a rigid body, right? I want to talk about the sum of the forces on a rigid body. And those forces right now are going to be they're going to be tangential forces, right? Forces, linear forces. They're not going to be radial forces. They're not providing centripetal acceleration. They're going to cause some angular acceleration. So if I talk about these tangential forces and the sum of the tangential forces, I'm going to get the sum of these mi, these little chunks of mass in the object, times ai, which is that tangential's acceleration. And if I break that apart just a little bit further to give me my angular accelerations, right, I can say that the sum over I of mi ri times alpha. Right, and alpha is that angular acceleration. R alpha gives me my tangential acceleration A. Now Ri times Mi looks a lot like my moment of inertia, right? I'm missing just a little bit of something. I'm missing an R, right? This is very close to I. It's very close to the it's very close to the moment of inertia. So let's take this and tweak it slightly. Let's modify it, right? Let's actually say, what if I take the sum over I of Ri times Fi, which are these tangential forces, that would give me, right, mi Ri squared times alpha. And now what I can say is that this is equal to I alpha. Right? I alpha. And again, I alpha, if we think about I and alpha as corollaries to M and A, F equals MA, well, that means that torque would equal I alpha. It's almost just a substitution at this point, right? But the big thing is that I need to modify the force, right? How do I modify that force? So we're calling it torque, right? Torque then has to be equal to R times F, but it's not just R times F, it's actually going to be R cross F. So it's really important to remember that these are vector quantities, and now we're taking a cross product. So at this point, I probably would say time out, go all the way back to chapter 3, open up your notes, and look at that vector multiplication stuff that we talked about right at the end of the last lecture. And I said this wasn't going to become important until much later down the road. Well, guess what? Now it's starting to become important. I'm not going to focus on the cross product right now. I'm actually going to save that for a lecture 5.5. Sorry that I'm doing these kind of in-between lectures, but I want to separate the new concepts from the review. So we're going to put a pin in the cross product right now, and we're going to go back. We're going to talk a little bit more about just this idea of R. In this case, R is the distance from our pivot to the application of the force. All right, and I have a cute little image here of a wrench, right? Wrenches, door handles, these are all really good examples of torques in motion, right? So if I have some sort of force, let's say I apply a force, I have this stuck a bolt here, and I need to just, I'm just going to shove my hand, my palm straight up on the end of this thing, right? I'm going to apply some force this way. Well, I would take my R, right, to be from the pivot point, which is the center of our bolt, to where I'm applying that force. So I have R all the way from the pivot point to the end of my wrench times F in this scenario. Now, what if I had a different scenario? What if I said I foolishly am really choking up on the wrench, right? And I'm going to try and shove that up maybe here, right, in the middle. I'm not going to probably be able to have as much force, but I'm also going to have R much smaller, right? Much smaller. So R and F are kind of playing together in this space. Now, I do want to take a moment and just consider another scenario. What if I pull on this thing? Or what if I just push on the inward on my wrench here? Right? What if I have something like this? Is this thing going to spin? Is this thing going to rotate at all? I don't think it will, right? I don't think it will. I think you'll be confused and confusing everyone around you what in the world you're doing with this wrench, right? But I don't think it's actually going to move. And that kind of keys us in on what this cross product does. We're going to remind ourselves in the next video that the cross product is maximized when I have an angle between my vectors of 90 degrees. So we have a toy model here kind of showing us what to do. We're going to talk about the direction that torque actually ends up turning in next time. I want to end us with just considering some conventions. All right, if I think about some R like this, and maybe I have a force going up like this, it's tempting to say that this is the angle between my vectors. It's very tempting to say that, but that is not correct. All right, if I'm going to be thinking about this cross product, and we can simplify the cross product as R F sine of phi. I'm using phi here instead of theta just to make it a little bit easier. The phi right? If I keep extending r, the phi is here. That is my angle, right? Another way of saying that is, what if I take my force vector and I bring it down here, right? What if I take my force vector and I bring it down here? That would be, that would be my angle phi, right? And that's what we approximated when we just had a force going up over here. Right, so just a note of convention there. You really want to make sure that you're getting the angle correct, otherwise it's just going to screw up your calculations later on. Okay, so that's where I'll leave it here with our introduction to torques. We're going to keep coming back to this, but here's a quick interlude to remind ourselves about cross products and an introduction to the right-hand rule. All right, see you back here in just a second.